As I mentioned, I know a lot of us have probably already done StyleGAN before, and I think that's totally cool. And if you get bored of me doing the same tutorial over and over again, please feel free to take off. But I do quickly also just want to mention, like, I think that what I think about or interesting about interpolations, or like how I think we connect this to the work we're seeing today, is like, what is the materiality of machine learning, and how do we begin to think about how a film could be made using those techniques or thinking about that. And obviously that's been the point of this entire class. But I think especially with today's videos, and watching those and thinking about like how we extend sort of the film materiality metaphor into machine learning, is kind of interesting. And I think a space that we'll be seeing lots of people sort of explore and think about over time. So really quickly, I'll share my screen. And so today's notebook is really going to be about latent spaces, and we probably haven't covered latent spaces before in this class. I know in many of my other classes that's like the only thing we cover, or like the thing we talk about all the time. So for some of you who haven't taken this class before, maybe this will be new. And I'll sort of, I do actually have slides today. I've tried to get away from this class of not having slides, but I think some slides will actually be helpful to understand latent spaces in particular. So I want to talk a little about sort of like my working theory of all this stuff. So we talked a lot about structural film today, which is sort of the like emphasis on film as a material, right? So like who's making the film? What's the mechanical process of making this film? Is it, shot on a dolly? Is it, in the case of La Region Centrale, like this like swooping like camera attached to, I forget even how it was made, but this idea of the camera being a fixed position, or the idea of a frame, right? The idea of, in many ways, the thing what structuralist film is about making the viewer aware that you are watching a film, whether that's through stuff like flicker, and sort of causing a physical sensation by changing the frame every 24 frames per second, or by like choosing a rather bland topic and forcing you to understand the structure of how the film is made, right? It's like a very low, long zoom, or thinking about how language interprets the structure of a film, those sort of things. So that's how I would talk about maybe structuralist film in particular. As we also talk about like this sort of happened at the same time that video art was becoming a big thing. And my knowledge of video art is far more limited. But I would sort of say like one of the things I think is interesting about video art compared to film is that unlike the 24 frames per second of filmmaking at that time, video was about sort of the signal, right? So like in the case of a lot of video artists like the Vasulkas or other people, what they were trying to do is they were taking a live signal in and they were distorting it in real time, right? And the idea was that time was sort of like, here's a live real time thing happening, and I'm altering it and altering the perception that you're seeing at that exact moment. We're like milliseconds off. Um, and I think that you could even like take that into like maybe what the current like algorave scene is, or like live coding experiences, where it's like it's really about the exact moment in time as people are presenting things, and it's about altering that moment as quickly as possible, right? So doing real time work. Um, so I think film, being a process where you have to shoot it, you have to then like get it chemically processed and then represent it. It's like a difference as well in the way that we experience time, or the materiality is different. The way we experience time is different. And what I'm going to posit in this session for today is that with machine learning, the next step is that like it may not be real time, it may not be film in like the sense of 24 frames per second, but what machine learning does, especially in the concept of latent spaces, is it gives us sort of a plastic time where time really has no beginning and no end. And what we'll be doing with this in this class, we'll actually be producing like little loops and things. And what we'll see is that like in the latent space and the way we conceptualize it, like you can move through this space at any speed or any time, and the whole thing just sort of like morphs and works it with itself back to what you're looking to do with it. And I think that that concept will change how we think about making film in the future, which is that like even today, like I guess we can shoot on some of these red cameras that shoot at like 200 frames per second, right? And we can sort of slow time down to like that. But like with a machine learning model and a digital experience, like we can actually create time in between time. And like I'm glad we didn't have to talk about my film too much, but like that was sort of the concept for my film, and You Are Here, which is like it's stretching time so far that it is actually slower than you're able to experience it, right? And I think like that is another way to think about how we approach filmmaking, how I approach time. And one of the things I think is really interesting about machine learning in particular is that there is this very plastic sensation. Maybe you get that too with 3D rendering, right? Because you can make anything as long as you can render it in light and speed. But even then, you're still saying, here are the key points where I'm animating a thing, or here is how a thing changes over time. And you have a very specific like sort of sense of time as you make it. Whereas machine learning really is like you sort of produce this space that can generate video, but like you didn't say how to shift things. You're sort of almost working with it's almost like working with clay, right? It's like you're trying to mold this thing to work with you and trying to get it to sort of like produce the film you're looking for. But in many ways, it's also its own little experience. So what we're going to do for today's lesson is we're just going to go through how to generate like video using a latent space. And I will talk a little bit more about what a latent space is, so that if you're confused by what I'm saying, hopefully that will be covered by the end of today's class. So I should also mention there are slides. You can click on the link here and open up the slides. There's also a very small portion of using StyleGAN 2. I wanted to focus specifically on just generating video from it. But if you're interested, there's a much, much larger notebook, as well as a ton of videos that I've done. StyleGAN tends to be the thing I know the most about and I've recorded the most about. So if you're looking for like more on sort of this experience, there's a lot more in this much larger notebook. So this is like just a little segment of it. Okay, so let's get set up here. So if you haven't already, make sure you run the first cell just to make sure that we're on a good GPU. I should also mention that if you do get a K80, there's a potential that you'll run into issues with rendering video. Probably the safe bet is if you do get a K80, for this demo, maybe download one of the 256 or 512 models. I'll talk about those in just a minute. That way you don't run into any GPU limits. Next is you want to make sure you run this cell. We'll skip the collab cell. Or the drive cell, because we'll just download it and watch stuff in real time, or like pseudo real time. And then we don't need to save a bunch of high-res files or anything to drive. So make sure you run this cell. This just installs the code in your repo. And the last part is we have to use a specific version of Torch, so it takes a little bit longer to run this. So just make sure you run that, and hopefully you're all set up. So the last step we need to do before we can start generating images and video is we need to download a model. So I've listed a bunch of different models here with the various sizes they're available at. So one thing to know is that models in StyleGAN are trained at a certain size, and when you render them back out, they render at that exact same size. So if you train a model on 256 by 256 images, the output will be 256 by 256. Now there's in the longer notebook, there's ways to kind of futz with that a little bit, but for the most part, that's the way to think about it. So in here, you'll see there are 256 models, there's 1024 models, and there's a 1512 model. So I'd say if you're on a K80, maybe try the cars model or the cats model. These all came from this really great repository, which I think we used for Lucid Sonic Dreams, which is a bunch of pre-trained models. So you can use any of these. Like what I'll probably do is I'll just use WikiArt. So what I'll do is I'll just comment out. If you just click on these lines and you just do Shift 3, you'll just comment this out so that those don't download. This does take a little bit of time to download all these models. If you want to, you can just download all of them and then run them. But just so I get a little bit less time, I'm going to just run this. So at the top here are some models that are available through Justin's site. The bottom cell here are models that I've trained, and you're welcome to use those as well. So you can see here we've got cats, painted portraits, abstract art, cars, and wiki art. And then down here we've got flowers, flowers on a black background, and then minerals. So you're welcome to play with those. If you do use my models, I just ask that you not share these outside of this class. This is a bonus for you guys paying for this class. And I guess my Patreon backers get these generally too, but I just ask that you not make these public to anyone otherwise. So you're welcome to play with any of these. I've downloaded the WikiArt model. If you want to download any of these, you can just go ahead and again comment out what you don't want, and then just run this, and it'll download those as well. Okay, and if we refresh over here, you should at least see one or two models. Like I downloaded the WikiArt model and I downloaded the minerals model. This should be fairly fast because we're doing server to server, so it should be decent. Next, there is a conversion of a legacy model. You might need to run this. If you get an error, let's just find out. I don't think you'll actually get errors if you use these models in the later steps. But if you do get an error or something, we might need to run this cell. If anyone runs into this issue, I'll come back to it. But essentially, all you need to do then is take the path of your model say copy path, and place it in here after source. And then what you want to do is just set the destination. So we'll just say like minerals dash converted. So this will just convert your model to the latest version. You probably don't need to do this, but just in case, this is the step to do it. So run that. That should be pretty quick. So if you do run into issues with some of the pre-trained models from Justin Pinkney, I might recommend that we do that. So we'll see. All right, so now we're pretty much set up. So now we're going to talk a little bit about latent space, and then we'll start to generate some images and videos. Okay, so what is exactly a latent space? So latent spaces are kind of hard to talk about because we're talking about really, really high dimensional stuff. We're kind of talking about the Hollis Frampton world of filmmaking, I guess. But essentially, the best way to think about latent space is that think about a space, like a literal like two-dimensional space that you can look at. And the thing to think about here is that at any one point in this space, there is an image, right? So the way that our GAN models have been trained is they've been shown a bunch of images. And what the model learns is basically to repeat those images back to you. And it finds the best location to place images in this space. So you could kind of do this manually, right? If I gave you 50 photos of, let's say, I don't know, cats, and I would say like, hey, group these or cluster these into a space. You might put all the black cats in one corner and all the white cats in the opposite corner. And then you might try to like blend like, okay, the Persians go here, tabbies go here. Like it's sort of that process, right? The model's whole purpose is to sort of sort these images and put them into the space in a way that like is coherent. So what that means is that any point in the latent space, has an image attached to it. So these are a bunch of random points in a space. And if I pick this one, I get a image of a person. And if I pick another space, another point, I get a different person, right? And the concept here is that the further away you are in this space, the more different your images should be. So if I pick a spot that is actually closer to my image, I should get an image that is pretty similar, right? So this person has slightly shorter hair, slightly different skin tone, maybe different eyebrows, that sort of thing. But we see here is that something this close should give us a pretty similar image. Whereas again, if we pick something really far away, we should get a very different image. So that's essentially the latent space. So what we're going to do is we are going to provide essentially randomized coordinates to the model. And the model will say like, okay, you want an image at this coordinate point. Here's what that image looks like. Now, the difference is that we're thinking about this conceptually in like a 2D or maybe a 3D space. The latent space by default in StyleGAN is 512 dimensions. So it's like a hypercube or like some other like crazy thing. And our brains really can't think like that, right? Like we have no way of like saying like, okay, imagine in 512 dimensions, I've sorted these images. But that's essentially what this model does. So what we'll ask for is when we ask for, we're going to use what's called a random seed. If you use processing or any other like programming language, you might be aware that a random seed is basically a way to replicate randomization. It's like a pseudo-random. It's not actually random. It always gives you back the same number. So we're going to use that to generate a random point in space, and then it will give us an image from there. So let's take a look at that first in this notebook. So in the notebook, here in testing and inference, what we're going to do is the first thing we're going to do is we're going to give it a path to our model. So what I recommend doing is if you downloaded one or maybe you downloaded multiple models, I should say these models are what the .pkl file convention is. Just copy the path for whatever model you want to generate from. So I'm going to use WikiArt. So we'll copy the path here, and we're just going to paste this in, and then we're going to run the cell. So this will just save a variable for us. So we don't have to constantly restate like this is where the model is. So we'll save this as a variable, and then we'll use it going forward. So what we're going to do first, we're just going to generate an image. And we'll see how images ladder up into video in just a second. But the first thing we want to do is generate a single image. We'll run this script called generate.py. We're going to tell it where to save the image. So it's going to save it out to some folder called here/out/images. We'll come back to truncation in a second. I would say for now, leave it 0.7, 0.8. We'll talk about what that means in a minute. And then here's where we're actually going to request our random parameter. So this is a thing called seeds. So we're going to ask for one image. We're going to just say like, give me the image at seed position 0, and then using my model. So this is that using that variable. So let's go ahead and run this. And the first time you run this cell in Colab, it's going to take a little bit longer to get set up because it has to install some code. So you'll see this thing called, it's installing a PyTorch plugin. So it's going to take a couple seconds for this to get set up. But essentially all we're doing in this case, we're asking for one image. And the thing about seeds, again, if you've used processing as random seed or maybe Python's random seed, seeds will always represent the same position in your model. So if I stop this notebook, restart it a week from now, and I load in my WikiArt model, the exact same model, it has to be the exact same model. That's really key. If I load in the exact same model and I ask for seed 0, I will always get the same image back. Now, what this seed actually stands for underneath the hood is like it spits out a 512 dimensional array that is a point between -1 and 1.0 that is this latent space. So StyleGAN's latent space is -1 to 1 in 512 dimensions. So this just generates that random value. So if I come over here and I go to out, and I go to images, and I double click on seed 00000, there is my WikiArt image. So it happens to be a face. So if you run this with a different model, you'll get a different image. If you run this WikiArt, you should actually get this exact image. If you don't, I'll need to think about why that would be, but you should get the same image if you use WikiArt. So obviously getting one image is fine, but I don't want to do this over and over again, right? I don't want to be like, okay, now give me seed 1 or give me seed 2. So what's nice about this particular model is that you can pass in a range of variables or range of numbers. So we could pass in 0 to 50. You could pass in 0 to 5,000 if you are willing to wait around to generate 5,000 images. On a K80, that's probably going to take you a couple hours. On a V100, it'll probably take me an hour or two. Or more. Actually, I don't really know how long it's going to take, but it'll take a long while. So maybe for this session, let's do something small. Let's just do 0 to 25. So again, if I do 0 to 25, I should get the 0 image, and it should always be the same. And then I'll get 25 additional images. So let's just run this. So maybe actually let's keep truncation at the same value and run this. I don't think I have the code here to do this, but you could actually look up what seed 0 equals in a 512 dimensional array. Now, none of us would know what that really means, right? It's going to be a big float number, 512 of those, and it just sort of be like, you imagine it as an x, y coordinate in like a 512 dimensional space. So, okay, so now we have 26 total images, and if I refresh my folder here, you'll see here are 26 images. So my usual step for this is that I will generate maybe 200, 500 images, and then I'll download them and I'll look at them. You can think about these almost as key points. So if you're doing an animation and you want to animate between points, you can use these seed values to say, I want to animate between this image at seed 0 and this image at seed 10, and I want it to do it in 15 seconds or something, or 15 frames or whatever. So that's what we're going to do next. So what I would recommend doing is, if you run the cell below, this will generate a zip file of all of your images. And what you can do then is you can just come over here, refresh the folder, and you'll see images.zip. You can download that. And this might take a little bit of time to download. What I recommend you do is, after this tutorial, maybe download a bunch, like 300 images. This is actually where it's probably good to have Drive. You can just move it, drag it into Drive, and then look at them there, or download them from Drive. For whatever reason, Drive is faster than Colab. So if you move stuff into Drive, you'll be able to download it and upload it faster. Who knows what they're doing some sort of throttling there. But what I recommend you do is you just download some images and then play with them and maybe like take notes on like, okay, I really like seed 0, I really like seed 15, because some of these images, like this particular image is, abstract. It's like not very, like, it's not clear to what it actually looks like. But you'll be able to sort of like begin to document like, okay, I really like this seed, I really like this seed. I could see this seed moving to this image, like, that sort of thing. So what we're going to do is we're just going to keep track of these images. And then what we're going to do is we'll be doing what's called interpolation. So maybe let's let this download while we talk a little bit about what interpolation is. So now we've been able to generate sort of individual images in this space, right? So this image here is maybe in the WikiArt model is my face. This image over here is maybe that more abstract one that we looked at. Inference or generating images is the process of just like grabbing one of these images. It's often called evaluation testing, generating new images from your trained model. So that's just what we did just now. So now we're going to look at, we're going to skip truncation. So we're going to look at interpolation. So the idea here is like, and this makes sense, right? Maybe intuitively, is if I take this image here and I take this image here and I travel along a line in this path, I should get something that animates, right? If I take very little small steps, the image will change slowly over time, but it should begin to navigate to a place where now I can animate between these spaces. So this is what we call interpolation. That's simply because we're taking 2 points in space and we're interpolating between them. So we're just going in and we're taking individual little points in this space as we walk from here to here. You will sometimes also hear this as a latent space walk, because walking from point A to point B. So this is what's called interpolation. So what we're going to do for the rest of this class is just like look at different ways to interpolate our space. Because again, remember that we've got lines, right? We can walk in a line, but with any walking or moving through space, you can do a lot of things, right? You could do something that's more circular. You could do something that's like a very noisy sort of like random walk. And we're also going to look at how to play with other things like truncation. So I will quickly talk about truncation as well. So if you recall, we had to set a truncation value. A truncation value is a kind of like trick of StyleGAN, where what truncation allows us to do is allows us to kind of force realism into the space. So the way to think about this is that because the model is both sorting images and trying to regenerate images from it, a lot of times what it will generate are very weird, like sort of amalgams of the images you give it, right? So let's say I give you an image of a bunch of babies, a bunch of adults, and the model doesn't really know what babies are or what images are or what adults are. It just sort of knows that these are facial features or pixel values. So sometimes what it'll do is it'll give you like a baby eyes on like an adult or, other weird things. So truncation is this technique of essentially trying to get to a more realistic effect. So here's an example of what truncation, if you basically were to take a single value and think about how we move through the truncation space, this is what happens to it. Oops, let's see. So what you see is when we start, we get a very realistic person, and then it moves out and it gets weirder and weirder and weirder and weirder, right? So like that's the truncation space. The way to think about this sort of maybe theoretically or just like in how we can work on this, like it's literally truncating the space, right? So if you imagine that maybe stuff at the edges of your model are more weird and stuff in the middle are like more realistic, truncation allows us to sort of say like, okay, zoom into this section, to this section. And truncation is often a value between 0 and 1, but could technically go infinite directions. The key to to know about is that if you set truncation to 0, you're basically saying I want the centermost point, which is essentially saying I want the most average image in my model. So if you set 0 for a truncation value and you ask for 50 seeds, every image will be the exact same because it's truncated the space to like such a small area that there's only one image available to that space. So in general, we'll use a value between like 0.5 and 1. 0.5 being more quote unquote realistic, and 1 being more like just sort of a generalized space of the area. This truncation value that we showed before the video here, I think this goes from like 0 to positive 2. So if you go into the positive range or like past 1.0, you're likely going to get weirder and weirder stuff. Maybe you want that, maybe you don't. But again, this is sort of the fun sort of plasticity of these models is like you've got a wide range of things and you can start to control them a little bit as you begin to play with it. So 2 things. So let's start by just looking at how to do a truncation interpolation. So that is down here. So here's truncation, what we call truncation traversal. The script for that is down here. So you use the generate.py script. You'll pass in a process of truncation. So this just does a truncation traversal. You will choose where to save your images. So this will do is it'll actually save out a bunch of images and it'll convert that to a video. And then you get a starting value. So let's start at 0. So that's going to be that like point in our space that is the most average image. And then where do we want to stop? So let's just go to 1.0. And then let's give it how often should I take a photo of that image essentially. So for this demo, I'm going to do something really quick. Let's do 0.5. That gives me what, 20? No, that gives me, I don't know. I can't do math today. I think that might give me 20 frames. let's see, 1 divided by 0.05, 20 frames. Okay, so let's make that a little bit smaller. Let's just do 4. That'll give us 25 frames. And then you want to give it a seed values, right? So this is going to be like, what seed image do I want to start with? Now, the important thing to know here is that when I generate my images, I generate it using a truncation value of 7.7. So that means when I actually start my truncation traversal, it's not actually going to be that image. But at some point, I will see, when I hit 0.7, I will see that image. So let's just go ahead and let's use 0, which was that face. So we'll use seed of 0, and then we're going to use our model path. So we'll run this cell now. You should also like choose your folder. So let's do trunk traverse, whatever. We'll run this cell. Now, realistically, if you're going to do this outside of this demo, you probably want to make this longer. You probably want to do something like 0.001, like that'll generate like what, 1,000 frames, 100 frames. So you might want to play with exact values that you use here. When this is done, it will save out a folder. So we'll go to out trunk trav, and you'll see there are all of our frames here. So if you wanted to just get an individual frame, you could do that. The nice part about this is that we also get a video. So this will download a MP4. This just uses FFmpeg under the hood to generate these videos. So here's my video. So that's obviously very fast because I only asked for a couple frames. You'll see sort of like, here's the most average image in WikiArt, I guess, for some reason. And then as we scroll out, that's probably the face I saw, give or take, in 0. And then it gets a little bit crazier as we go out. Now, in this case, it looks like the face is zooming out. That is not always the case with truncation traversal. It just happens to be maybe with this model that it does do like the zoom out effect. Again, the kind of fun of these models, as well as the frustration, is you don't really know what's in them. It's just a bunch of numbers, and you kind of find it by playing with it more. So in the case of WikiArt, WikiArt's a very popular model for StyleGAN. I would guess a lot of people have sort of like learned how various things act in it. I know with my own models, like I've sort of learned like how the models act or react based on different interpolations. So that's truncation traversal. So the important thing is that it's really not going from point A to point B. It's just changing a single point, and it's sort of like calculating that truncation value as it goes through it. Any questions there? All right, moving on to finally getting to interpolations. So interpolations, what we're going to do is we're going to pick 2 points in our path, or maybe more than 2 points, and we're going to be able to walk from point A to point B. This will essentially give us an interpolation. So let me just go through my images here really quickly and see if I've got another good face to work off of. So I'm just going to open this. So here's seed 0, seed 1, seed 2 looks like some boats. So there's another face. So let's do 0 to 7. So one thing to know about these models is the random seed is quite literally random. Like these, so seed 0 and seed 1 are not close to each other. They are random distances from each other. So a lot of what I tend to find works well is generate a lot of images, just so you can sort of see what's available to you, and then begin to play with the different points in space using these seed values. So let's go from 0 to 7. And let me just see if there's a couple other images in here. All right, so let's do 0, 7, and 18. Okay, so interpolations are here. The path for this is generate.py. We're going to save this out to video 1. We will skip space. We'll come back to talk about space in a minute. Because I know those images were generated at 0.7, I'm going to leave this at 0.7 just so I make sure I'm getting the exact same images I asked for. The process is interpolation, so again, it's just a walk. And then here's where I want to set my seeds. So what did I say? I said 0, 7, and 18, right? So this is going to give me a 0. It's going to go from seed 0 to seed 7, and then from 7 to 18. And what is not listed here, but I should have listed, is the frames function. So if you pass in -- frames, you see equals, and let's say 240. So what this will do is, by default, this video gives us 24 frames per second. So this will be a 10-second video going from basically it'll be 5 seconds to go from 0 to 7 and 5 seconds to go from 7 to 18. So if you want to control this and make it shorter, you could do 120. That's going to be twice as fast. You can make it twice as slow. That'd be 480, that sort of thing. So this just generates like how long the video should be. So let's go ahead. I'm going to make this a little bit shorter just so we've got the time here. So let's do that, 120. And you should discover that like depending on your GPU, this is rather fast, right? Like this is generating like an image less than a second. Okay, so while this generates, let's talk a little bit about what that space thing meant. So you'll see up here, I use this thing called space equals z. So StyleGAN StyleGAN's a little special compared to other models in that there's what we call the Z space and the W space. The Z space is the like sort of default. It's what every GAN model essentially gives you as a latent space. The W space is a little special. So let's take a look at how that works. So I want to show everyone this image. So I don't think we've done this yet in this class, but let's see if I have. Take a look at this interpolation and tell me what's wrong about it. So remember that we're going from this image to this image. So everything in between there should essentially be an interpolation. So if you look at these images in the middle, something is wrong with them in a couple places. So can anyone say what they think might be wrong with these images?
Eyeglasses on one of the figures.
Yep. So obviously this person doesn't have glasses. This person doesn't have glasses. So how are glasses showing up in here? There's a couple others. So maybe see if anyone can catch anything else.
Mouth.
Mm-hmm. Right. This mouth is closed, this mouth is closed, and this mouth is open. How did that happen? So this is a thing you'll hear people talk about, which is called entanglement. The problem is because we have, even though we see it as a high dimensional space, the models themselves are actually kind of like 512 dimensions is too small. Like it's too small to hold all of the world's data, essentially, is the way to think about it. So what ends up happening is it kind of squishes part of the data together. And what happens is as we move through that space, we can sometimes get areas or clusters that aren't really correct. So the Z space is what's known as sort of the entangled space, or just like a space where like it doesn't really do everything the way you expect it to. And what the StyleGAN creators did is they also created this other space called W. And what W is essentially it's a mapping of our 512 dimensions to something that is actually 18 times 512. So it is a way to take our small dimensions, move it to a bigger dimension, and hopefully we get better mapping or better space representations. So this is an example of what that interpolation looks like in W. And you'll see here our mouth stays closed, our guy doesn't get glasses here. And there's even some other interesting things, which is like the hair apparently animates in a way that is more correct, quote unquote. You know, other things like skin tone tends to feel more even, like that sort of thing. So in general, when we talk about the W space, we're talking about what we would describe as more like accurate or more readable interpolations. But you know, in an artistic sense, like maybe we actually like some bumps in the road, right? Like maybe we like a little bit of noise as we travel through the space, especially with some like art. Like maybe that's a place where you want a little bit of noisiness, a little bit of other things. So these models, you can access both. You can say like, okay, here's what Z looks like, here's what W looks like. So the only difference between this cell, like we could literally just copy this cell and paste it down here, and we could switch it to Z space to W space. So if we switch it to W space, we should get a more correct, a more linear interpolation that should be correct. So if we run this cell, I'm just going to download this video real quick so we can look at them. we should get a more accurate like linear interpolation essentially. Okay, so here is our z-space linear. Okay, so we went from this position to this position. I would guess maybe one of the things we might get out of the W space is see how it kind of bounces down first and then moves up. I would imagine that what we might get is like a more smooth movement directly up and toward the center. And then similarly, we might get a little bit of a better movement from here to here. It's kind of like bounces between these spaces. So we'll see what we get with the W space. One thing I also want to mention is you might notice that this gave us 0 to 7 to 18. A really nice trick is, let's say we want to loop this video. One of the tricks we can do is we go back to our Z space. If we change our seeds from 0 to 7 to 18 and add 0 back at the end, what we get is we get a full loop on this video, right? So we go from 0 to 7 to 18 back to 0. So if you want to like upload this to like a 15-second loop to Instagram, it'll feel like it's sort of endlessly repeating, which is kind of a cool trick. So it's as simple as just making sure that your first seed and your last seed are the same in a loop that way. You might get one frame if you're like really picky. You might get one frame extra, and you might want to like go in and edit that out. But most people can't tell. So that's just how you do looping. So looping is just as simple as like making sure that your first seed equals your last seed. Let's see, is it still rendering? Still rendering here. Let's see, what else do I have in my latent space video that I want to talk about? Oh, so one other thing I want to talk about with linear interpolation is we'll look at how to maybe solve for this or work around this in the future. If you choose points in space, right, and we don't really know where these spaces, where these points are physically located, if you choose 2 points that are really close to each other, and you ask for 30 frames between us, and then you pick 2 points that are further apart, right, so maybe between here and here, what you're going to get is this interpolation is going to feel slow. It's going to feel slow going from like very close points, walking slowly there. This is going to feel fast. So one of the problems with linear interpolation is controlling speed. It's actually very hard. It tends to be a big challenge, and there's ways to sort of operate around it, but with pitfalls. So just know that like your speed in a linear interpolation model will sometimes feel kind of jerky. It'll go like slow and then fast and then slow and then fast, and you'll be kind of like, how do I even that out? And we'll look at some additional interpolation methods where you could do that. But for the most part, it's kind of a challenge of these spaces that have yet to be solved for. So just be aware that like these will produce like sort of slightly different animation speeds between each of these points. Let's take a look at our W video. Where did W get saved? Content out video 1. Oops, I think I overwrote my video. That's all right. We'll deal with that later. And so the other trick is it's kind of hard to play 2 videos side by side on your Mac without having to like load them into something else. But let's just try scrubbing through it. So we will open up our W next to our Z. So on the left here is my Z space, and on the right here is my W space. So let's remember we scrub through here, and there's this kind of weird bounce. We get up there to there. So let's see how different this is with this. So scrub, yep, as I called it. I've done this enough now that I know. There's none of that sort of move down and then back up. It's really linear. It feels a little bit smoother. And then likewise, it feels a little bit smoother up there. And you will see, like, if we move maybe between this, you can see there's definitely differences in these animation spaces. So I think it's worth like animating both and just sort of seeing what you get. It's pretty easy. You're waiting 5 minutes to generate these videos, but it's just helpful to sort of see the difference between these. And this is again one of those like areas where you can tweak various little details and get different results out of it. So that is the W versus the Z. And you'll also, I think you should notice, let's see, did I close those out? I didn't. Okay. So let's see how this one animates. So it feels a little fast right there compared to the other speed. Again, the W space should be smoother. It should feel a little bit more like continuous motion. Yeah, I think it does. It's so hard to tell with some of these things because you're animating so many things at once. But I would say in general, that feels a little bit smoother than the other one. So that's kind of another thing to know is you could use the Z space or the W space to get different types of motion as you begin to animate those. Any questions about Z versus W? Okay, cool. We've got a couple minutes left here, so I'm going to quickly run through a couple other tools. One of the things we're going to look at is a noise loop. So as I mentioned before, like, this gives us more control over those points, right? It allows us to say, I want to go from this point to this point to this point and back to this point. But the challenge is, like, sometimes you just don't really care. Like, you just want to see as much of the space as possible. So a noise loop is literally going to just give us sort of like, excuse me, it's going to give us a wavy line. And it's just sort of going to start in one point, do a whole wavy stuff, and then end up back where we began. So let's take a look at how to generate a noise loop. Set is down here. So we'll see here again, generate, and we'll use the outdir of this path. We will then use truncation of 0.7. We'll use the process of interpolation, and the exact interpolation we're going to use is the noise loop. Now, noise loops do not take in seeds because seeds don't. You can't really control the noise loop in a seed space, right? We can't really say, well, we could, but it gets really tricky to say, like, I want to go from this point to this point in this loopy fashion. So instead, what we sort of do is we just say, like, let's just pick a random point, a single random point, start there, and then we'll move from there. So with this, we've got a random seed, which is just 1 point. And we've got this thing called diameter. Diameter is sort of it's hand wavy more than it is a real mathematic diameter. But basically, you can think about it like the larger your diameter is, the wider the space is going to be. The smaller your diameter, the smaller the space is going to be that you're going to be interpolating through. So in general, I've got some notes here. I think this should be like between like 1 and 5. So just sort of think about that. The further you make your distance, your diameter, the more like you are to hit those weird, like sort of like nebulous, like noisy regions. Maybe you want that, maybe you don't. So I tend to stick with like something like between 1 and 3 in this particular script. So with this, we're ready to run this. Let's go ahead and run this. But there is also one last thing which I want to mention is you set frames using the frame count. And let's set this to be a little bit shorter this time. So the difference here between frames in this sequence versus frames here is this frames is frames per step. So it's 120 times 2, right? So there's 2 different steps. This one is overall frames for the entire video. So just know that, like, this is the frames work slightly different between these 2 tools. So we'll go ahead and run this. I tend to find that I really like doing noise loops once I've finished a model, and I just want to sort of see what the space looks like, right? Because what's nice is this will just like randomly traverse the space, and it will give you lots of like little nooks and crannies as well as just sort of like what the actual space looks like. And that's just going to help give you a better sense of like sort of what your model space looks like. So it's kind of nice. It's like just like a random walk through the neighborhood, just sort of see what you have. And then maybe once you have seen like, oh, I see how wide it is or like how diverse different corners can be, then you might want to go in and begin to tweak and pull out individual seed variables. And while this runs, I'm just going to go ahead and run the next cell. We'll talk about this in just a second, but this is for running a circular loop. So unlike a noise loop, which is just going to give you a specific sort of like noisy path, this is going to give you a much smoother path. So again, we'll sort of set a diameter. The challenge here is diameter works differently in this context. I've got a note here between 50 and 500. I've got up to 800 here. So this is a much larger value, just the way the math works inside of the thing. We can go ahead and run this too, so you can see the difference between a circular loop versus a noise loop. And so the circular loop is, I don't have an example of it here. You can imagine the circular loop as literally like a attempt to be a perfect circle. It turns out in hyperdimensional spaces, there is no such thing as a perfect circle, but you get a better approximation. So essentially you get a value that is like a nice sort of like smooth interpolation through the space. And what this uses is it uses a 3-point circular construction. So you could actually, this doesn't do it here. This will generate random seed values. So it'll generate 3 random seed values and then generate a circle within that path. But you could actually pass particular seeds. So let's actually do this. Let's see, seeds equals 0, 7, 18. We'll run this later and see how different it looks. But this should essentially hit these points while also creating a perfect circle through the rest of it. So math in hyperdimensional space is kind of weird, but just know that it kind of works, is the best way to explain it. Okay, so our noise loop finished here. So let's take a look at our noise loop. So see, this gives us a lot more range of different images. The speed is also very jerky, right? Like as we're hitting different points where it's like, hitting a curve and we get something that speeds up, slows down. But again, I find this to be just kind of fun. It allows you to see a lot of the space of the model. So know that the frame count times your diameter sort of gives you an approximation of speed, or like how much of the space you're going through, right? So if you have a really large diameter and a small frame count, it's going to feel really fast. If you have a small diameter and a high frame count, right, you're going through a smaller amount of the space in more frames, it's going to feel slow. So just know that like that's sort of the space you're working in, and to think about that. Let's take a look at our circular loop video. And what's nice about these looping structures is they do automatically loop back on themselves as well. So whereas with a linear structure, you have to sort of say like, yes, I want this to loop. These other ones, they just sort of loop by mathematic properties. So here's my circular loop. So one thing you'll notice is that there's this little moment in here where it bounces, almost kind of comes back to itself. That's because of this high dimensional space, right? In a circular space, you would imagine it to be more like even, and it would never go back on itself. Turns out high dimensional spaces are just really weird, and like you'll still have a little bit of this bouncing back on itself that happens. So it's kind of worth playing around and just sort of seeing what you get here. I believe, let me double check this. I think circular loops can work in both Z space and W space. So you could also try a space of W. I'm like 90% sure this works. You could do a space of W, and then that will also, like, might get a more even path through that. I think by default it might do Z. I'd have to check my code to make sure this actually works the way I expect it to, but you could play with that as well. So lastly, I probably won't go into this too much because we'll cover a little bit more about this next week. But there's a thing, we'll definitely talk more about layers in a model next week. But just know that GANs tend to have different layers. A deep learning model is essentially a bunch of layers in itself. And what you find, or what people have found, is that you can play with the individual layers in addition to the latent space. And you can start to generate really weird videos. So we'll talk about this a little bit more next week, and it'll make more sense next week about what's actually going on in this. But if you just want to have some fun, you can run this flesh digression script. It's got the best name in machine learning. And what it's going to do is it's going to make really weird distortions of our latent space. So this is finished. We'll download it and we'll take a look at what the video does. So let's see, that just finished. This one saves into a weird place. It always saves into your StyleGAN model. So just go in here, and then your name will be also something kind of funky. It'll be circular dash and then a bunch of date times. Oh, that's also really big. So again, we'll talk about this more next week, but remember, or like just know that deep learning models tend to have different layers. And in particular in GANs, what tends to happen is the lowest layers tend to be really small. They tend to be like 4 by 4 pixel layers. And then the top layers are the actual size of your model. And the model goes through like a upresing, upsizing function as you go through the image creation. So your lower layer, if you play with that lower layer, you're essentially playing with like a really blurred version of your image. Like imagine like scaling a large image down to 4 by 4 and you get like just little pixel values, right? So if you play with that value at that smaller size, which is what we're going to do here, what you end up with is like then a big image that is really weird because of all of those little pixelation changes. So it's kind of a cool process. This is almost finished downloading. What I recommend doing is just play with these notebooks for this week. This is probably going to all we'll cover for StyleGAN, but if anyone wants to know more about StyleGAN, if you want to learn to train your own model, that sort of thing, I have a ton of videos on that material. I know Sean, I think you're already doing that. I think Ben, maybe you said you were doing your model. Was that true? Yeah. Okay. So if people are interested in training your models, I have a ton of materials on that. It takes time, so you probably won't be able to do it between now and like show and tell, but if you're interested in playing with that, we can definitely look at that. So really quickly, I just want to show you how fun this image looks like. So let's see. Well, actually, it might be kind of hard to tell with WikiArt because we don't really have faces. If you play with this with a face model, you will definitely see how weird it is. But essentially what happens is you get different corners of the space that do different things. It's actually really hard to tell with this particular model. But if you play with it with like cats or cars or something that is more like obvious, you'll see that the model gets distorted in very weird ways. So I would recommend just playing around with these, getting a sense of sort of how the latent space is constructed, how you can play with time, how you can play with speed. If you want to get really crazy, you could set one of the frame counts to be really, really high and literally watch it like change pixels at a time, which is kind of fun. I mean, that's essentially what the video that I showed at the very bottom of our playlist is essentially using a model that stretches pixels into like really, really lengthy time periods. So it's that particular video is actually only, I believe it's like 20 frames, but it stretches those 20 frames out using a machine learning model into 50 minutes. So you can like see like the patches and swirls as this thing extends into longer periods of time. So it kind of goes with this idea of like, I think time is really plastic in machine learning models and allows us to sort of play with that time. So maybe next week we'll pick up this a little bit. I'll just discuss a little bit about what flesh regression does. And then the code here at the bottom, if you want to play with it, allows us to take all these videos and sort of combine them into one video. So if you want to do a bunch of like little cuts of things and then put it all together, both of these will do that. You probably want to play with this one instead of this one. This one requires you to like keep count of things, whereas this, if you just pass in all the paths to individual videos, so you'll just put each video in double quotes and then comma separate them. This script will actually just figure out how to generate the concatenation feature, how to combine them all into one video, and then you'll run this cell below it, and it'll just combine all the videos together. So this is kind of fun. Again, maybe you want to do like a really short, like maybe a couple short videos, and then you want to do one long video, and you could begin to create rhythms by just like generating different latent space animations and then combine them together. So maybe you can have some fun with that. So we'll pick up with this again early next week. Next week, we're also going to talk about particularly how a machine sees. So again, I sort of think it's interesting that, structureless films are sort of built around how humans see, right? Like the whole idea of a flicker video is essentially like messing with a human's perception. And so what we'll talk about next week for the rest of the class is we'll actually look at how machines perceive, and then we'll actually play with some of those ideas and concepts in a thing called neurocellular automata, which I think will be kind of fun. We'll basically get back to what we talked about in week 1, which is like making static images move. That's what we're going to do for next week. So it should be kind of fun and it'll be cool to play with. So definitely play around with latent spaces. If you have questions, let's talk about them co-working. If you make something cool, share it to Slack. And with that, we'll wrap up for the day. Any questions before we call it a night? Okay, cool. Well, I'll see everyone in co-working, and if not, I'll see you next Thursday. All right, bye everybody.
Thanks, Garrick.